Okay, so this talk is about deep referral learning applications. Basically, it's a big overview and is with some of my understanding. So, okay, let's start it. So, in 2016 March, AlphaGo, that's a worldwide news headlines. So everybody knows this. That's why referral learning gets to the of the crowd. So now everybody in AI probably should know referral learning, and this time we'll talk more about it. Referral learning, a very brief introduction. There is a agent, and the agent interact with the environment, and at some state, and it takes some action, and it gets some reward from the environment, and it will transition to the next state. So it will iterate in this kind of interactions with the environment, and so the objective is to maximize some long-term rewards. This is a very general model, and many real-world applications can be modeled in this way. Actually, this reinforcement is from the animal learning, classical conditioning is the Pavlov's experiment with the dog and foot and the ring. So referral learning has a root in animal learning in optical control, and also something called trial and error. That's why Sutton and Anibato, they are the pioneers of this field. So basically those three threads. So it leads to the current modern referral learning, in particular the deep referral learning. So referral learning is related to many fields, just like we mentioned that it related to the conditioning related to reward system. It also related to, say, optimal control of operations research, machine learning, and of course, computer science, engineering, mathematics, economics, psychology, neuroscience. So yeah, it related to so many fields. So it can be applied to many problems in those fields, and at the same time, it can help to improve some understanding in those fields. For example, in neuroscience, people have already found that some mechanism, they are basically like the, say, TD learning, some algorithm in referral learning. So yeah, that's fantastic. Yeah, this is basically the categorization of those terms. So we have deep learning. Deep learning is now a popular word, a buzzword. Everybody knows that. And there is super learning, there is unsuper learning, and referral learning. So in super learning, there are labels. We have X, we have Y, we have pictures, and we have the label, say, a dog, a cat, or something. And then we try to learn some algorithm from those pictures and the labels. And when a new picture comes, we can predict what it is. It's a dog, it's a cat, or something. And for unsuper learning, we don't have labels, and so we try to learn some structure from the data. And for referral learning, just like we mentioned, we actually don't have labels, but we have something. We have something called evaluative feedback, the reward. And we can learn the optimal policy based on those kind of reward. But the reward, they are not labels. And deep learning can work with all those different machine learning schemes. And when we have deep learning and referral learning work together, then we have deep referral learning. That's something we are talking today. Yeah, and these terms, they are a part of the machine learning, and machine learning is part of the artificial intelligence. And yeah, there are more details. Yeah, if you are interested, you can, say, for example, check my overview. Or I recently also write an application, a referral learning application. They are on archive. So David Sirot gave hypothesis. Is basically say something like referral learning and deep learning can achieve AI. So we achieve AI by combining deep learning and referral learning, basically deep referral learning. So referral learning is enough to formalize the problem of intelligence. And deep neural networks can represent and learn any computable function. So deep learning and reinforcement learning can solve the problem of intelligence. Yeah, this is kind of a strong hypothesis, and there are some debates, but it's from David Silver, and he's a lead. He basically lead the project of AlphaGo, so it makes some sense to at least to some extent. So, but things are evolving. For example, deep learning. There are also some issues, challenges for deep learning, for reinforcement learning. For example, they may not be able to handle, for example, the say symbolic stuff or reasoning or logic. But things are happening and evolving. So we may not take a static view on those things, but we may see them as evolving and new technology will be coming. Here I introduce something called DQN. For AI, for reinforcement learning, usually a usual test bed is games. And one of the popular games called arcade games. It's actually dozens of games, 50 or something. And in 2013, people started to achieve astonishing results. They use a single algorithm, a single set of hyperparameters, and single network architecture. For deep learning, we need deep neural network, so some network architecture. So they use single algorithm, single set of parameters, and single network architecture, and they achieve very good results on many of those games. And some of them, 30 or something, they can beat human level results. That's in 2013, and after that, people started working on this and make a great achievement. And last year, there was a paper called Agent 57. They can achieve much better results. They can beat human level at all those 57 games. So it improved much of the deep Q network, the DQN algorithm. And basically, this is the state of art. And actually, this Agent 57, I think that's a very good paper to recommend for people who want to know more about reinforcement learning. It basically integrate many techniques in deep reinforcement learning. For example, from the very start of the deep Q network, and then they combine the short-term memory and exploration and extractive memory and meta learning. So they put them together and make them work. And also they use some new metric, performance metric, how to evaluate a program. It's called something called a fifth percentile. Basically they are looking for the worst. The fifth percentage worst. They are looking for those worst. Sometimes the average may not represent the truth. For example, for the income, me and say Elon Musk, the average is very high, but it doesn't make lots of sense for myself, right? So if we are looking for say 5th percentile performance, then if we can have very good performance on the 5th percentile, then basically the performance for basically all the program will probably be very good. Rather than using the mean or average to evaluate the performance. Yeah, so this Agent 57, I think that's a very good result for this other games. And the techniques are general, so it's probably helpful for other problems. And basically at the same time, there's another paper called First Return, Then Explore, Go Explore. And it also studied those games and also study. Actually, I think it's the results basically was better than the Agent 57. This one used some technique. Basically, it used just from the title. It's something called first return. It basically used some search techniques like from the classical AI and make it work for this problem. The classical AI have achieved amazing results like the like Deep Blue and beating the chess champion, world champion. And this paper combined those classical AI techniques to the deep reinforcement learning and achieve stunning results for the archery games. And yeah, this is for AlphaGo, but it's a lot. And basically, I want to say AlphaGo is based on deep learning, reinforcement learning, and something called Monte Carlo research. And that's a very good result. Yeah, I won't say too much about it now. And if some people want to know more detail, we can come back later. Actually, in these slides, there are actually many. There are actually 80 pages, 80 slides. So for many of them, I will go pretty fast. Here I list some games, say StarCraft, poker, curling, Dota. This one called something called Kite Flag, and this called something called Hide and Seek. Basically, reinforcement learning has applied to those games and achieved very good results. Yeah, so in some papers, I list some applications from some papers, and if you can see, they are basically very diverse and many potential applications. So yeah, basically this say actually game is an abstract of the real world. So games to AI is basically like fruit flies to genetics. Yeah, so games can be everywhere, and many problems can be modeled at games. And if we can achieve good results on games, then we can probably apply them to some other applications. So game reality is broken, or in the Chinese translation is something like games is changing the world. And there's something says about gamification. Many things can be regarded as games. Actually, for example, in everyday life, say a wife and husband, they don't want to do wash dishes. So maybe there's a game, and in the game they can, there are some incentive for them to, maybe they can play games, and the game can help them to decide who will wash the dishes. Or even in the work, the say options, salaries, promotions, these kind of the incentives and kind of the games. So for people and for the company or for the society to work together. So in some sense, the society is a big game, multi-agent games, and how to design the mechanism for the society, for the game to work together, for some better goals. So, yeah, okay. So I talk about I'll give a brief introduction of the deep reinforcement learning and some very good results, and I will go over some successful applications actually very fast. So I just want to point you to some successful applications. So some pointers, and if you are interested, we may talk after. We may talk a little bit, or you can go to check those results. There's something called multi-unbounded, and there are already some applications, and one of them is from Microsoft. They apply to, for example, click-through rate, for say news recommendation, for say advertisement recommendation. So they can achieve say 25 to 30% improvement. Yeah, this number is pretty big actually. Especially if you are thinking that's a billions dollars business, say 25, 30%, that's very big improvement, and 18% revenue lift in the landing page. So this is from Microsoft. It can be this technique can be applied to say news website, technical support assistant, cloud controller, many applications. This is also yeah, multi-unbounded is a simplified version of reinforcement learning. It doesn't have state. It has action. It has reward, and it will go over many times. Yeah, we have k arms. We go around, and in any round we choose arm, and the arm generate reward, and observe reward and repeat. So we want to maximize this total reward. Yeah, this is a simplified version of reinforcement learning. It doesn't have state, but it can still apply to many applications. And I think the good news is for multi-unbounded, the theories are pretty mature, and there are also many mature applications. For example, this is also for Microsoft. In the real world, in the software, in traditional software, there are many say pipelines, and there are in the pipeline we go this step to next step. They are usually pretty clean. But in machine learning software system, there are many issues, and they identify some issues, say some failures. For example, in reinforcement learning, we need to have the delay. Yeah, maybe I should say that, for the supervised learning, we need, say, XY, we need some data, and we need the label. So the data, yeah, the input X and the label Y, they construct this, constitute this data point. But for reinforcement learning, we need state, action, reward, next state. We need this kind of tuple to form a data point. So we need the reward. But in the real life applications, sometimes the delay, the reward may be delayed. For example, we click a page, we may stay there for say several minutes to read the news. So the reward may come maybe several minutes or even hours later. So the system need to handle this kind of say delay. But there are also other failures or issues. So Microsoft, they abstract these the functions in this system and implement this. So I think this is a good illustration of how to apply or extend the current practice in software engineering and apply this into the machine learning or reinforcement learning applications or software systems. Yeah, so I think this is very interesting. And yeah, there are some Microsoft, they are also apply this to some customers support board, and they summarize license. Usually people publish papers, and usually they report successful stories but not failures. So this paper is about those lessons. So I think that's a very good results for people if you want to implement this kind of say reinforcement learning system, and these are the pitfalls to try to avoid. And we learn lessons from them, and we try to reduce this kind of cost. Yeah, and reinforcement learning application at Microsoft, we mentioned already several slides, and there are more in Microsoft. Based on that decision service, they have already launched this personalizer service, and people can use it. And they are already customers, worldwide, from say Mexico, from Russia, from UK. So I think it's I think it's worthwhile to check what Microsoft has done on the reinforcement learning. And Google is a gen tech company, and they have done lots of things about machine learning, about reinforcement learning, and they have done like the RecSim. So just now we mentioned those applications. They are basically reinforcement learning for recommender systems, and for the if we have simulation, then we can generate data easily, and they develop this kind of simulation for the recommendation. And for Facebook, yeah, they already make this deploy this in their system, and there's something called reagent. Previously they call Horizon, but now Horizon, I think they just now recently I checked, they now rename Horizon for their metaverse, and now they call this project reagent. So basically they can do like notification, in the Facebook, like messengers or say events, they can notify users, and yeah, they open source this. So yeah, that's basically I think the first major one from those big company, and they open source it. Yeah, and this one I think needs a special attention, especially you are from the operation research world. You know, just now we mentioned like the recommendation that's basically still pretty computer science. But you know, in the operation research, you know, there are lots of scheduling stuff, and this one is from Didi. You know, it's like say Uber it's like Uber in China. Yeah, it's a very it's a big company, and so you know every day there are many passengers. They want to look for taxis, and how to match them. So that's you know just one scenario, and they have already done this ride hailing order dispatching. And yeah, they receive a very good result award from the INFOCOM. They call Wagner Prize winner. And yeah, there are lots of resources online from say Tony Chin. They have tutorials, they have workshops, and yeah, they have papers. So yeah, that's pretty interesting to look at. Yeah, I think I will go fast to speak more from my point of view. So this one from Google is about you know balloon makes this work in the real life, and this is from this is a very amazing work. It's a robotics you know for like quadrupedal, and so this one is a blind. There's no computer vision stuff, but it was pretty well. Here there's only one picture about you know those very challenging terrain, but it can work in this kind of robot can work in say forest on the mud in vegetation, you know, very challenging terrains, and it just use reinforcement learning. So robotics it can work now for you know at least for this kind of scenarios. Yeah, this one you can see many stuff, and from the leftmost column you can see many applications, especially you know from the say computer systems is from the very bottom circuit design to the very top like SQL database query optimization. Yeah, basically you know this is yeah people develop this kind of environment to study how to apply reinforcement learning to those computer system applications. Because you know the simple message is reinforcement learning can be applied to almost all the problem or applications in computer systems. Yeah, I think if you you know Google search you name some application and Google search it basically and put reinforcement learning there, and basically you can find those days. Yeah, there are so many different kinds of applications. Yeah, this one from several applications from Google is from neural architecture search. Is about data auto augmentation, and it's about device placement. For example, we have a TensorFlow program. We want to schedule this on say GPUs, CPUs, memories. We want to schedule this to make it efficient. And this one is from chip placement. You know about the you know the hardware chip, chip design. Yeah. And recently there are two papers that's I think pretty amazing. This one is called auto ML0. It's basically machine learning algorithm itself from the using some machine learning techniques. You know, basically this is about meta learning, learning machine learning by machine learning algorithm. So, and last year they have done this on you know machine learning algorithm, and recently I just found they have done this for the reinforcement learning algorithms. Yeah, they you know basically they use machine learning to find machine learning or reinforcement learning algorithms. That's kind of the kind of yeah that's very amazing, right? So we can you know we can find even optimal algorithms using this kind of techniques. Just consider, you know, for the AlphaGo, we can, you know, learning the optimal strategy or very good strategy even from scratch. And now people are trying to do this for the machine learning itself. Yeah, so that's very very amazing. Yeah. And actually, now the many problems they are related to combinatorial optimizations, and there are many exciting work already on this in this field. Yeah, and it's about a multi-agent autonomous driving. It's a simulation environment, and this is about game testing. Just now we mentioned lots of about game playing. For game playing, reinforcement learning or AI is now very strong. But for game testing or software testing, that's still a different story. But these days, people already have done very good work, and we can automate those game testing or software testing using say reinforcement learning or AI techniques. And for education, instructional sequencing, and for this is another education example. It's basically something called intrinsic motivation, and try to motivate people to learn out of the fun or interest rather than being forced to learn those things. Yeah, so it goes naturally to something called flow, and if something is not very difficult, not very easy, and we are interested in that, so we have the interest, we have the fun to do this, and we have the flow, so we can do this better. And if we can apply those kinds of psychology principle, say flow, or and then say we can use those principles to design the how to automate the content generation of say video games or other things. But here I just present the video game example. And if we can quantitatively define fun and anxiety, based on those psychology principles, then for reinforcement learning, if we have state, we have action, we have reward, then we can define this problem, formulate this problem, and then we can solve it. That means we can generate those content. Nowadays, some games they generate from some AI programs. And say mobile health, that's also an interesting application. And yeah, and finance, there's a simulator. It can do say trading, portfolio, those things. And there also for economics, for the tax policies. And here I think it's another domain. It's from a control. Yeah, control people will recognize this. The model predict control. And this one is for the data center cooling. It's from Google, and they apply reinforcement learning combining with classical optimal control techniques, the MPC, and they can achieve better results. Actually, just like we mentioned in the very beginning, reinforcement learning and control has a strong connection and big overlap. And this one for electricity distribution, this is a simulator, and yeah, so people have already done something in this field. And drug design, actually drug design, I think it's probably interesting to look at. It's maybe this one may AI or reinforcement learning may help this kind of drug design to make breakthroughs. Yeah, AlphaFold, that's related. Although this one has not used reinforcement learning yet, but reinforcement learning may be used sometime for this application. Yeah, COVID-19, that's was something we are currently experiencing. But I think COVID-19 is a very good application area for reinforcement learning. And I think those days, the current practice, basically they are now using some kind of, like the SEIR model, this kind of simulation. But for people in reinforcement learning, that if we have this kind of simulation, then we can use simulation to find the optimal policy, just like AlphaGo. But nowadays, I think most people in the say public health, they don't do this way. So I think there's a big room for people to improve for COVID-19. But if we can also consider the the interaction between this epidemic and the economy, and we put those together and to use deep learning to optimize something and with some constraint. So yeah, I wrote something. I actually spent several months on this topic, and I wrote something. It's not published, but it's just some write up, some manuscript. I put it on the attain.ai. If you are interested, you can check. Yeah. Just now very quickly I mentioned many applications. So next I will talk about the challenges and opportunities. So for software engineering, machine learning, AI, reinforcement learning, to make them work, we need some software system, and software engineering is a natural field for this kind of issues. And for traditional software systems, we have some kind of a pipeline, and we have basically somewhat clear defined the steps for the pipeline. But for machine learning and for reinforcement learning, it will become much messier. And from here you can see, although people can identify some steps, in this kind of pipeline, but we can see this kind of the loops. We have to go back from some step to some early steps, or even to the very beginning. For example, we know that when we train some model, we find something, then we may go back to the feature to do the feature. For deep learning, maybe you can automate this feature, but sometimes we still want to do feature engineering. But sometimes we may even go back to the very beginning to collect the data, or even to redefine the model requirement. So that's a problem with machine learning or reinforcement learning. So there are still many issues, and but I think that's good. That's good. People are starting to look at those issues, and say from the software engineering angle, and especially for machine learning. And that's another piece of work. People identify something called technical debt. So that's they will cause problems for machine learning software systems. And there is already a survey about deployment of machine learning systems, and that's, I think, something interesting to check out. And I think that's pretty good. People are starting to look at those issues from the software engineering angle, and I think that's good for the widely adoption of, say, machine learning, and especially reinforcement learning. But for reinforcement learning, it's not many work yet. So now those software engineering, they are basically machine learning, and software reinforcement learning still needs more work. So this is an open question. Maybe that's a project for for companies or for researchers. For deep learning, we have the ImageNet, we have the ImageNet event, ImageNet event. So the AISTATS achieve like the half the error rate of the last year's result, like from something like 29% to 15%, like this kind of achievement. But with the help of this kind of ImageNet, the data set. So this set is important for deep learning. Well, how about for reinforcement learning? Do we need some good data set? Nowadays we have something, but maybe we still need more to improve the understanding of reinforcement, and also for software engineering. We have done lots of work, some work for the machine learning, but not too much for reinforcement yet. So maybe we want to do more about how those software engineering principles for the reinforcement software system. So that data set and software engineering, that's basically an open problem for people to think about. Maybe there can be interesting work from this, and yeah. Good news is, I think there are now some kind of competitions for reinforcement, and so using those we can have more data and more scenarios to study reinforcement in the real world, or something close to the real world. And if we have those data, there are some technique called offline reinforcement or batch reinforcement. We can use those collected data to train the algorithm and achieve good results. Yeah, some people summarized the challenges of real-world reinforcement, and let me see. Yeah, so basically summarize those, and they design algorithms and design experiments to test those, and give some suggestions. So basically, it's a paper, and it's already accepted to the machine learning journal, and it will be published soon. Now there is a archive version on the internet. Yeah. Yeah, this one I want to say it's about actually this is basically about the UI, user interface, and yeah, there are basically this is basically about from the title you can see it's about motivation, engagement, and thriving in the user interface, user experience, and this is based on something called self-motivation theory. Just now we mentioned the flow, and this self-motivation theory, both of them are somehow, yeah, they are part of the positive psychology, and so those kind of principle from psychology, they can be applied to this kind of UI or maybe applied to real function. But on the other hand, maybe reinforcement learning can help those systems. We can use AI reinforcement learning to find better design for, say, game design, for game content, or for the UI design. So there are two angles to look at this thing. But that's maybe another open problem. You can see I put a question mark. So. But I think probably that's interesting, something interesting to look at. Yeah, and yeah, there are some people trying to understand this problem. For example, from the say robot learning, robot is if we can have a very very capable robot, then we are closer and closer to the AGI, artificial general intelligence. So, but nowadays we are still working hard on this. And Kipling gave us some talk about some challenges about sample efficiency, about generalization, about composition, about incremental learning, and give some suggestions in this this part of these issues. Yeah. And there was a discussion about interesting discussion about prior knowledge structure in machine learning. It's a bit lesson or better lesson. Research basically say we don't need lots of those kinds of prior knowledge. We just need some general method and the computation. AlphaGo is probably a good example for this kind of argument. But some people also say, no, we need more human ingenuity. And for example, say convolutional neural network that's designed by people. And there are still some issues about, for example, it's easy to fool AI system to recognize a stop sign as a yield sign or 55 speed limit sign. So that's a problem, right? So we still need lots of human ingenuity to design the AI system, and the computation may not go as fast as earlier, so it may slow down. But maybe both of them are correct. They are from different angles and different stages of the AI system. Yes, maybe for problems like say Go or those kind of games, we can use general method. But for some problems like say education, like say even game design, we still need lots of human ingenuity to do that. Yeah. So, and recently people from AI borrow ideas in psychology and the system 1, system 2 cognition. Actually, this gave some a professor in psychology a Nobel Prize in economics. And a good news is used for learning. There are already some work using this kind of principle from psychology, from neuroscience, and applied to some important issues like sample efficiency and inductive bias. So if we, for these days, when we train a reinforcement learning system, we need lots of samples. That means computation, means data, means lots of means resources. We require huge resources to do some reinforcement learning work. For example, AlphaGo. For example, those say auto machine learning or auto reinforcement learning. Yeah, we need lots of huge resources to do that. So if we can improve the sample efficiency, then we can have better results. We can have more efficient learning algorithms. And there are also issue about inductive bias. Actually, just now we mentioned that should we put more inductive bias into the system? But if the inductive bias is correct, then it can achieve much better results. I think it's something like, when people are learning, we learn, say, English, we learn French. After we learn English and French, it's probably easier to learn like German, right? So we already built something into the system, and when we see something relatively new, we can borrow some old skills to learn something new. So yeah, that's something about the inductive bias. And in reinforcement learning, there are techniques like something called episodic memory and meta learning to help improve the sample efficiency and help improve the inductive bias. And also an issue about causality. That's an important issue, and I think that's it's very important, and it's also important for for inductive bias. For example, if we can use causality to help build some compositional representation. Yeah, something. One thing about deep learning, why it's so powerful. One thing is about representation. Deep learning can help achieve very good representation of the data point. For example, from this the left corner. This point, if we use Cartesian coordinates, we need some circle to differentiate the blue and from green. But if we put them into the polar coordinates, we can just use a straight line to separate them. So straight line is much easier to find than a circle. So that's about representation. But nowadays, in the AI systems, things are getting more and more complex. So we may need say graph neural networks to represent some say graph. For example, combinatorial optimization problem. Many of them are probably from the graphs. So maybe we can use graph neural networks to help improve the performance. And just now we mentioned the causality. If we can using some disentangled representation using some causal inference, then this kind of representation can help the downstream tasks to learn more efficiently. Yeah, so this representation is still a big issue and a big challenge. But we are making great achievement in this direction. Yeah. And yeah, interpretability, that's or explainability. That's also a big challenge. And there are some achievements, but we are still working on this, especially for reinforcement learning. There are some work. There is even a survey paper. So yeah. So there are some achievement, progress on this topic. And some people summarize guidelines for reinforcement in healthcare, but probably that's also interesting for other applications. Basically, it suggests to access to all variables influencing decision making and to look at the effective sample size. Big data is big data, but we want to use the effective data, not just big data. We want to interrogate reinforcement learning policies to behave prospectively as intended. Yeah. And yeah, people discuss about do no harm. It's like for healthcare, but I think that's also for AI. Ethics, morality. We maybe for doctors we need to take OAuth, but maybe for AI practitioners, we probably also need to take some kind of OAuth, so to follow the ethics. For example, for the privacy, and but yes, for big data, privacy of big data, but for AI, for example, we don't want to develop say killer robot. Yeah, so there are some boundaries we don't want to cross. Yeah, just now we mentioned something, and they are related to constraints. We want to satisfy those constraints during exploration and also for the operation. And we want to treat off multiple objectives. And for example, for autonomous cars, we want to satisfy the safety. Also, we want to make it efficient and make it comfort. So, these are multiple objectives. So we want to satisfy them. And maybe we want to optimize one and satisfy the others. And so in deep learning or in the Markov decision process, people are studying constraint MDP, and yeah, this is a theoretical foundation for this, and we can build system based on those theories and make it satisfying those constraints. Okay, so now we talk about something about the business world. Yeah, people from say Andreessen, Horowitz, they talk about from the AI AI business, but they are somewhat related to the refining. So basically, there still is a low gross margins, and there are scaling challenges and weaker defensive modes. And for the AI machine learning refining, they are both software and services. For the internet business, it can scale very fast because the software can replicate very easily. But for machine learning, there is still the property of services. We still need people to take care of some corner cases to tune the system. So it's still hard to scale. So we need to think about those things when we to make machine learning, AI, refining to make them in the practical world. And we need to consider about model complexity. We need about data complexity. We need to think about variable cost, about services, and about building the defensibility in this new business. Yeah, and Andrew Yin, he's a very good researcher, a good business people. So he's a good in many things. And so he gave 2 talks recently. One about bridging AI's proof of concept to production gap. Another about ML ops from model-centric to data-centric. I think some message from him is that machine learning machine learning algorithm is just a small part of the machine learning system. You can see from the left figure, this machine learning code is just a tiny part of this whole system. So we need to think many components of this system. And maybe previously people focusing on model, but now we need to focus. We need to shift the gear and focus more on the data. Sometimes we have some model, and we try to find better data to make the model work rather than trying to refine the model. Yeah, but probably both are important, but maybe data is more important. Just like some people say, for data scientists, 80% time is about logging data, and so Andrew here mentioned that data is so important, so we need to make it data centric. And yeah, Chaba gave a summary of a discussion about the math and macro misconception in refining. It's a talk in a deep learning day at KDD 2020. And yeah, Dimitri Pachekas, he's a professor in MIT. He's a leading expert in object store, in OR, in refining, and he is especially positive about refining, and I think that's very excited. Yeah, although there are still challenges, he also admit concerns about that. Yeah. And Warren Powell is he was a professor in Princeton, and he has done lots of work in the optimal research and optimal control from that angle. And he recently talked something about the relationship between, say, reinforcement learning, MDP, optimal control, those things. And I think that's something interesting to look at. Yeah, and he also has a recent book he's still writing about reinforcement learning and optimal control. Yeah, so John Lanford and his colleagues gave a tutorial about theoretical foundation of reinforcement learning in Fox. Fox is a theoretical conference in computer science, and he gave a tutorial. And recently, Sutton gave a brief remark about, he mentioned something. He mentioned something like the AI for the information processing machine. We need to have computational theory. We need to have representation and algorithm, and we need to have hardware implementation. And he gave a remark about reinforcement learning is the first computational theory of intelligence. Yeah, this one is probably debatable, but this from Sutton. So, yeah, I think also good news from. I think I regarded this as a good news. From, say, McKinsey and from HBR, Harvard Business Review, they are publishing articles about reinforcement learning. They are basically supporting reinforcement learning. So McKinsey, there's a article. The title is "It's Time for Businesses to Chart a Course for Reinforcement Learning." And for Harvard Business Review, the title is "Why AI that teaches itself to achieve a goal is the next big thing." The next big thing. So basically it says reinforcement learning is the next big thing. So probably especially you are from a business side, and these two articles I think highly recommended to look at. Okay, there are some understanding for me. So when reinforcement learning is helpful, basically I think it's when big data are available. These days we are still working with big data. We are working with machine learning, and so far reinforcement learning is still using big data to train the model. So we need big data. So the data may be from model, maybe from good simulator, or maybe from interaction with the real system. So for the natural science and engineering problems, usually these problems are well designed. We have clear object function. We have a standard answer, and it's straightforward to evaluate. So in this case, where reinforcement learning will be very helpful. And the good example is AlphaGo. And there are other applications in combinatorial optimization, in algorithm research, in optimal control, and like drug design. So I think these are pretty promising, and we just need maybe more resources to work on this. And there are also problems from social science and humanities. In those problems, usually there are humans in the loop. So it's usually influenced by the psychology, by behavioral science, and so usually these are subjective and may not have a standard answer and may not be easy to evaluate. For example, for the game design and game evaluation and education, these are usually social science and humanities. But I think good news is the concept like psychology, like something we mentioned, intrinsic motivation, self-determinist theory and flow may help to serve as a bridge between R and AI with those social science and humanities, and by defining the real function. If we have real function, we have state, we have action, then we can define the reinforcement learning problem, and then we can find some reinforcement learning algorithm to solve them. Yeah, so applications are rare, since reinforcement learning solves sequential decision-making problem, and many problems are sequential decision-making problem. Even they are not sequential at the first glance, but we can make them like into a sequential decision-making problem. For example, the neural architecture search problem, that one we can use reinforcement learning to do that. And reinforcement learning can intelligently automates previously manually designed strategies. Previously many strategies are designed based on heuristics manually. So reinforcement learning has a potential to automate intelligently those strategies. Yeah, so reinforcement learning can be basically everywhere. I put computer system here. I put science, engineering, art, humanities here. So basically everything can be approached from reinforcement learning. I put some resources, and yeah, we organize workshops. We organize this machine learning special issue, and we have 2 workshops already, and we have this year is coming, and we are still call for papers, and it will be in July 23rd. And so we have excellent, very excellent panels. We have six panels from theory to practice. Main topics: robotics, or recommended system, interpretability, and foundation, and also research to real life gap panel. So yeah, I think this one is highly recommended. So check it out. We have a web page here. So yeah, and these are the papers already accepted in the machine learning special issue. And yeah, I spent maybe a couple of minutes talking about my understanding why reinforcement learning is not widely commercialized yet. Deep learning is already many people know that it's very popular. Everybody talking about deep learning. It's basically the same as AI. That's actually a mistake, but many people regard it deep learning as AI. So why? Just now I mentioned that reinforcement learning is so powerful. So why reinforcement learning is not widely commercialized yet? Okay, this is my understanding. I think one reason is there's no AlphaGo moment in practice yet, no killer applications yet. Although we have those successful applications, but these are not something like breakthroughs. Say, for example, for the DD application, they have say like 1%, 2% improvement. But that's maybe not the headline news results. So if we have this kind of results, like the say EGNight, like the ArcNight, like the deep learning, right? Say face recognition or image recommendation. So if we have this kind of this moment or this kind of application, then people will pour the resources or money in to this reinforcement learning. But now we don't have this yet. And also there are still challenges with implementation, algorithm, and theory. Actually, this is already applied to, this also applied to deep learning, but maybe reinforcement learning is a little bit more challenging for this. And also for software engineering, system deployment, technical debt. And also for the business model, is software plus service, and low gross margin and scaling issues, defensive modes, those problems. And we still lack of resources and say talents, compute, and funding. So this probably kind of a chicken egg problem. We don't have killer applications, so investment VCs, they won't pour money in. But if we don't have enough resources, we cannot make it happen faster. So but good thing is big companies, they already put lots of resources on reinforcement learning, so we can have good results already. Yeah, for the there is a slow adoption of new technology, especially for the traditional industry sector, for example, for the manufacturer. And they're also about technical rules about it should be AI plus or plus AI. Probably expert from say the traditional sector, like say manufacturer. If expert from manufacturer, he knows both the business and the AI, then that's probably more effective and more efficient. And AI can be helpful for this. So there's an issue about technical root. And about learning curve, reinforcement learning is harder than deep learning to learn, and there are like many many say algorithms, many terms to learn, and it's related to say optimal control to neuroscience, psychology. So it's more complex than say deep learning. So we still need more education and training, and yeah, I think other people, we try to help other people to understand refining better. Yeah. So refining doesn't work. That's not correct. Refining has lots of successful stories, and so the refining, the time is coming, and there may be not another AlphaGo moment or killer application, but refining is permitting slowly and gradually, and is promising, although it's still challenging. Okay, yeah, that's my talk. Yeah.
Great, thanks. Thanks Yuxi, for the presentations. I think there are some questions in the chat. I just quickly remind everyone, you can post questions in the chat. If you prefer to speak, to ask questions or make comments, feel free to raise your hand. We can unmute you.
There are quite some questions. Let me see. Did you review those questions, or maybe you can pick some first? And
okay, yeah, sure, go ahead. Let me basically.
Well, I mean, you can pick some first. That's why I didn't look at those questions just now. Yeah.
Okay. The first one is I think this is from Edward. You said the reinforcement learning helps define the objective, and deep learning helps optimize the objective. Can you go into more detail on how the two types of learning interact?
Oh, okay. Yeah, this is a very good question. Actually, this is from the slides about. Let me go back to that slides. Just 1 second. Yeah, this is basically from David Silver, and oh, this one. Yeah, for refining, we have state action reward. So reward, and this reward, the objective is built from this reward. So refining help define this reward. For example, the reward, for example, the goal. For the goal problem, for AlphaGo, the objective is to win the game. So it's natural for the refining framework. We have this kind of reward and objective. And for deep learning, deep learning is a way to define the problem, define the, for example, especially the representation. So the representation and the objective, they work together. So that's one way. I think that's one way to about this, how they interact. Yeah. So probably David Silver probably have more to say, but for a short answer, I think refining, deep learning provide this representation. We use say CNN, we use say RN or something to represent this problem, and refining define this state action reward, the objective, and then we use some optimization method to achieve the goal. Yeah, basically. Yeah.
Next question is from Amit. He's asking how to get started in reinforcement learning for industry applications.
Yes, I think okay, that's a general question. Here I present several examples. I think this one is kind of industry applications. Say model predict control. That's from say data center, but that's one thing. And yeah, I think it depends on how much you know about AI, about learning. But maybe I recommend these two. One is from this Dimitri Protakis. This is he has lots of things on his webpage, and also from Warren Powell. He also has lots of things on his webpage. Especially I think from I think both of them have lots of applications. And for Warren Powell, he has a course. I recently I checked that a little bit carefully. He has a course, and he has has many applications and using his yeah, although he don't call them all of them not exactly as following, but they are very closely related to reinforcement learning. So I think that's one place to check out about how to apply reinforcement learning or say stochastic optimization to those industry applications. Yeah.
So the next question is, what is an example you have heard of for reinforcement learning that is not deep reinforcement learning?
Okay, so basically this is about reinforcement learning or deep reinforcement learning. Deep, and maybe I want to say the difference, So say reinforcement learning can be, yeah, so what's the difference? So reinforcement learning can be tabular. That means, okay, so there are, say, value functions or there are policies. So the value function and the policy can be represented as tabular as some functional approximation. When the problem becomes large, we need functional approximation. And for the functional approximation, we can make them linear or nonlinear. So deep reinforcement is a nonlinear type of functional approximation. So the tabular case, we represent the problem, the value function, or the state action, the value function, the policy in tabular. Then that is not deep. It's not using approximate. That's exact if we can solve. And if we use linear functional approximation for value for policy, although the problem may be large, but we can use linear function or use say something like say decision tree support vector machine. If we don't use deep neural network to combine with reinforcement learning for say policy, for value, or for representation, then we have non-deep reinforcement learning. Yeah, there are a lot. Yeah, so deep learning is somehow the recent thing. After the deep learning become more popular. Although before that there are cases, but these days deep learning becomes popular. But actually there are lots of reinforcement learning they are not deep. Yeah.
Okay. So by the way, I see Ari he posted a link for the reinforcement learning book on applications. So I guess there is a lot of other applications in that book. So if you can go to the chat, I think he posted the link into the chat. Thanks, Ari. If you see more applications.
Okay.
So the next question from Taran.
Actually, I can see that. Actually, yeah, I can see that. No problem. Yeah.
Oh, okay. So should we go to the next question?
No. I mean, I can read it. So you don't.
Oh, okay. You can read it. Okay.
Yeah.
You can go ahead.
Yeah, I think that's also a good question. Yeah. So do I need to repeat it, or maybe you repeat it?
Yeah, maybe
some
it's
people
better
may not
just
read
read the questions.
Yeah. Yeah. I mean, maybe you can read the question. So yeah. Do you want? Oh, sorry.
Oh, you wanted me to read it? Okay. So for next question from Torren, he's asking, how does reinforcement learning play a part in recommendations and personalizations? Are there any industry standard strategies for algorithms around this?
Okay, that's a okay. Yeah, that's a good question. So yeah, so I think reinforcement learning nowadays getting more and more important in recommendation and personalization. Before reinforcement learning, people using other techniques like corruptive filtering, those kinds of techniques. But nowadays, people are working. I think there's a strong trend. There's something called, actually I mentioned that, multi-unbounded, or something called contextual bounded. It's about 10 years ago. People say, if you check Li Hongli, he published a paper using contextual bounded for the news recommendation Yahoo. At that time, he was in Yahoo with his colleagues. And nowadays, lots of people are using contextual bounded for the recommendation and personalization, for news recommendation and say advertisement and YouTube. There are quite some things happening in this, and also recently people are using the full reinforcement learning, state action reward, this kind of reinforcement learning for the recommendation and personalization. And industry standard technology, or I think contextual bounded. I think that's something, if you want to try reinforcement learning personalization, I think contextual bounded is something you should try. That's basically a standard. And for the reinforcement learning part, I think that's still evolved. You know, there are some. I think they're basically using some standard reinforcement learning techniques. For example, all policy evaluation, offline learning, say counterfactual evaluation, and you know, like those popular algorithms. For example, the say Q-learning. For example, the soft actor critic. You know, I gave some examples earlier, like from the say Microsoft. Maybe I go back. That's probably easier, right? So I can go back, and there are several actually. I think reinforcement learning for recommendation, that's pretty mature. So this one is related to that question, recommendation and personalization. So this one related, and this one related. Yeah, this chatbot is also, and many things here is related to that. And this one, recommendation simulation, on Facebook is also related. And yeah, so yeah, several of them you can see from Microsoft, from Google, from Facebook, and many places. So I think say contextual bounded and reinforcement learning is a standard in reinforcement learning in recommendation these days. Yeah. Okay.
Okay, so next question, we probably need to go a little bit faster. I see quite a few questions. So the next one is from Dave. What's the difference between model-based and model-free reinforcement learning? And what is the model that's being referred to in these terms?
Okay, yeah. So this is so basically, in reinforcement learning, model means, you know, the dynamics model is state, action, reward. Next state, you know, this is a dynamic, and there's also a reward function. You know, from this state, take this action, and what kind of reward we have. So the model basically refers to the dynamics of the system and the reward function. These two are the model. So if a reinforcement learning algorithm has a model, for example, for the AlphaGo, we have the model, so we can basically build a simulator and gather data from this model. But in many cases, we don't have model. The reinforcement learning can work without any model, just interact with the world, so collect data. The data is in state, action, reward, next state. If we collect those data, we don't need the dynamics and reward and yeah, we don't need the reward. We don't need the dynamics. So we can use those data to learn. So this is model free. But in this case, we still need reward function. Yeah, so basically model is about dynamics and the reward. And model free means we don't need the reward, we don't need the dynamics to learn the optimal policy. Yeah. Okay.
So the next question from Mohammed from Japan. He's asking, I use deep reinforcement learning in my research to control batteries in microgrids. Cross entropy method works for me, but Q-learning does not converge until now. My question is, why in the cross entropy method as popular as Q-learning?
Yeah, this question is too detailed. Yeah, I think there should be many issues. So yeah, I have to admit I cannot judge from, you know, this level of description. Probably we can take this offline if possible.
Probably they need something like a debug.
Well, I have my emails there, and feel free to ask me with my email, from my email. Yeah.
All right, so the next one from Josh, he's asking, how would you compare reinforcement learning and the causal inference problem to make decisions?
Yeah, so yeah, basically, recently there's a tutorial about reinforcement learning and causality, causal reinforcement learning. So I put it here. Let me, okay, just okay, here. You can see there's a causal reinforcement learning at ICML 2020, very recent one. So reinforcement learning and causality, they are related, although they are not the same. They are related. For example, in the on policy case, basically reinforcement learning is about is about intervention, is about counterfactual, but causality is also very powerful. So I think they are complementary. So yeah, maybe a short question is they are complementary, but they are also overlap. But I think a good resource is this causal reinforcement learning tutorial, and yeah, there are some people working on this. Yeah.
Great. So the next question from Chester from Singapore. He's asking any use cases of deep reinforcement learning in predicting non-payment of bills for fraudulent payment.
I think yeah, this question actually I had a brief discussion with my friend these days about anomaly detection. I think basically I think this problem still this anomaly detection problem. One thing is there are papers discussing about this. Another part I still think at this stage probably non-reinforcement learning techniques like say deep learning, like the classical machine learning techniques probably are better for anomaly detection. So somewhat at this stage, I'd like to refer to those. And actually, there's a recent survey by, let me see, by this professor. You can see Thomas Dieterich. You can check his Google Scholar. He has a recent survey about anomaly detection. I think probably that's a direction to go. If you want to try something new for research, reinforcement learning is something to go. But for practice, I recommend the classical machine learning techniques, yeah, for anomaly detection. Yeah.
Great. I think Chest also have a follow-up question. So I guess you probably just answered. So basically, he's asking, is it the case that supervised learning works more effectively for non-payment of bills?
Yeah, I think so. So yeah.
Right.
But if you want to do research to publish papers, reinforcement learning is something worth to try. Yeah.
Okay, another one, this is probably our last question, from Chen. He's asking, thank you for Dr. Li for the holistic introductions. Could you elaborate the connection between reinforcement learning and model predictive control? How to put the constraints to the action? Okay.
Yeah, so I think basically I recommend this paper, although I don't agree with it fully. So this table is from a paper. I think it's from this one, reinforcement learning overview of recent progress and implications for process control. I think that's should be pretty good, but there are something I don't quite agree. Yeah, I think you have the video, so you can check the detail, or you can check the paper. That's probably since we have some time constraint. And also for the, let me see, for the how to put the constraint into the action. Okay, so that's why I put this page here. Okay, yeah. So I put this. Yeah, I think this also something people are working on this. If you check, say Chabas, he has a blog about this, and also this paper this paper is on arXiv, and there are also people working on say SafeRL. I think that's somehow a big yeah, some people working on safe reinforcement learning. If you check those, you can see people how do they put constraint into those actions, and during exploration and operation. So yeah.
All right. So okay, I see one more question coming. Okay, let's take this the last one from Ari. He asking what are some good realistic industry examples and methods where you have seen promotion of curiosity and novelties by reinforcement learning explorations be much more beneficial than traditional supervised machine learning or deep learning methods?
Okay, let me see. Let me read a little bit. What are some? Yeah, I think, yeah, that's a good question. I think this one probably serves an example for this. Let me see. I think for this one, for the traditional MPC, I think, yeah, traditional MPC, I think they can also do some adaptive things. But, for refining, exploration is kind of a central part for refining. And for this work, I think one point is, researchers using the exploration techniques from refining to help MPC, and they don't have an exact model of the data center cooling system, but they can using those exploration techniques and to collect more data and to refine the model and to achieve the performance better and better. I think this is kind of the example to answer this question. And let me see. Traditional machine learning, deep learning. Basically, I think this is from also a bird eye view. Traditional machine learning or deep learning, they are basically one shot. We just do this and we just make this decision. We just is one shot is myopic. But for reinforcement learning, it's thinking about long term. It's thinking about many steps in the future. For example, for AlphaGo, right? We're thinking for the last, whether we win or not. But for machine learning, for the traditional machine learning or deep learning, we may just for example classification or regression, we just think for the current, maybe the myopic. Usually, I would say usually. So reinforcement learning has the yeah, it's by nature